Okay, good afternoon, everyone. I hope I'm clearly audible. So this session is on the CoCoSo method. Uh, I'll directly skip to it. I hope that by now you are familiar with what are alternatives, what are criteria, what is a benefit criteria, what is a non-benefit criteria, and so on. I hope that all of you are clear with this. So I'll directly skip to the CoCoSo part. Okay. So the method that I'm going to explain today is called as the combined compromise solution method or the CoCoSo method. So it is a relatively recent method. So it was developed by Morteza Zardani and his group. So this method basically is an amalgamation of two different methods, methods which are like very primary methods. For example, we have the weighted sum method and the weighted product method. So these two methods are very primary methods. So the CoCoSo, what it does is that it takes some inspiration from both this weighted sum method and weighted product method and combines them in such a way that the resulting solution that we have is more robust as compared to these smaller methods. Okay. So here you should note that there is also another method called the Waspas method, which was also derived based on the inspiration derived from the WSM and WPM. But the CoCoSo method is much more robust and much more complicated or much more sophisticated as compared to the Waspas method. So Waspas is also a very old method as compared to our CoCoSo. So CoCoSo was developed within the last 5 years. So basically, what we have seen so far. Am I audible, guys? Am I audible, right? Okay, okay, okay. Thank you. So basically, any kind of this MCDM methods, by now you have learned that all these MCDM methods, they start with a decision matrix. Okay. So how do we come across the decision matrix? So decision matrix is either collected if you are suppose say someone from the engineering sciences, maybe from mechanical engineering or civil engineering or electronics and so on. So most of the times your data comes from your experiments. Okay. So you collect this decision matrix, and suppose say you are from the management side. So then you collect the data through surveys or maybe through different publications which are available in form of suppose say technical reports and so on. So you collect this data and you formulate it in form of a decision matrix. So this is how a typical decision matrix looks like. So this decision matrix is composed of, as we know, some rows and columns. The rows here are the alternatives and the columns here are the criteria. Okay, so criteria are nothing but kind of objectives that you have. Okay, so this criteria or this objectives based on which you have to take a decision that which is the best alternative and so on. Okay, for example, in science in engineering sciences we have gone a one step beyond than going only finding out the ranking. So in engineering sciences what we do is that other than finding out the ranking, we also do something called the parametric optimization. Okay, what we do is that once we have the total or the final result in form of a crisp matrix, what we do is that we try to delve a little more deeper and we try to also find out the optimum parameters from the final output. Maybe that is also something that we can show here in a later part. Okay, so this is basically the decision matrix as you have seen in multiple sessions that you have so far. Now, what we do here is that in most of these methods, the primary step is or the first step is you normalize it. Okay, so depending on the whether you are using a benefit criteria or whether you are using a cost criteria, you normalize it. So if you have the benefit criteria, you use this particular formula where you take the entity or the cell value minus the minimum of that particular column or that particular criteria, and you divide by the range of that particular criteria. I will show this also in Excel, but I'll quickly try to review these formulas once. And then next is the cost criteria. So cost criteria is like suppose say uh, you are operating a company, and suppose say in that company you want to maximize the profits. So that is your benefit criteria, and you want to minimize the operating cost. Okay, so that will be a cost criteria or non-benefit criteria. So the formula for the non-benefit criteria is this one. You take the maximum value in that particular column or that particular criteria, and you subtract the individual value or the cell value from it, and you divide it by the range of that particular column. So range is nothing but the maximum minus the minimum. So it tells you that what is the amount of deviation between the best possible value and supposedly worst possible value. Okay. Next, As I told you, that this particular CoCoSo method is an amalgamation of the WSM, that is the weighted sum method, and the WPM, that is the weighted product method. So what we basically do is that we find out the WSM parameter and the WPM parameter, which are nothing but the SI index and the PI index. So the SI index is the summation index, which comes from the WSM method, and PI is the product index, which comes from the WPM method. So these are the simple formulas that we have. This is simply the multiplication of the Wj is the weight that we have for each of the criteria. Again, as Professor Prasanjit sir explained in the previous session also, and maybe in the even the sessions before that, you have known that these weights we calculate it by different kind of methods. Maybe we have the entropy method, ASP method, and so on. So overall, we have two different sets of methods, which we call as the subjective method and the objective method. So from this, we collect or we calculate the weights, and then we go on to apply the other methods like CoCoSo or Marcos and so on. Okay. So again, in the scope of this particular lecture, we will not delve into how we have calculated the Wj value, but we'll just assume that the Wj values are given for us. This can be calculated by any of the other methods. So once you multiply the Wj or the weight value with the individual cell value, then and you take the summation of the entire row, then you have the SI value for that particular row. Similarly, if you do that, if you take the cell value and you raise to the power of the weight, and you take for the entire, and you take the summation of the uh, entire row, then you have the product index. Okay. So next, you calculate three different appraisal scores. Okay. So you calculate the KI value, KIA value, KIB value, and KIC value. Okay. So this all this KIB, KIC, and KA value, KIA value, all these are calculated based on your this SI and PI values. So as I told, SI and PI are the simple index values or the simple appraisal scores which are calculated by the WSM and the WPM. Okay. So as you can see, that WSM and WPM are fundamental to the working of this particular method. So unless you solve it by using WSM and WPM, you will not be able to move forward in this particular method. So once we have this, then we can easily calculate the KI value, KIB value, and KIC value depending on by using these three different equations that we have. Interestingly, you'll see a parameter here called lambda, okay, which is present in KIC and which is not present in KIA and KIB. So this lambda is kind of a tuning parameter. Okay, so the value of this lambda it changes between 0 to, it can change between 0 to 1. So basically, what are these tuning parameters? These tuning parameters basically tells you that what is the amount of importance that we are giving to one of the methods. For example, as you can see here, lambda Si plus 1 minus lambda Pi. So it means the summation of both these should be the weight or the amount of importance that we are giving to both of these is equal to 1. Okay. So suppose say if it is 3, if we put lambda 0.3 here, so here automatically it will be 0.7. So it would simply mean that we are giving 30% importance to the weighted sum method, and we are giving 70% importance to the weighted product method, right? So that is how we do the tuning of the lambda. Again, how to take the value of lambda, that is again another question that we'll see in the later part of this session. But typically, in the original manuscript also, it has been suggested, and in most of the work that has been done in CoCoSo, so typically what they do is that they do a equal compromise for this, and they take lambda equal to 0.5, which simply means that we are giving equal kind of importance to both weighted sum method and the weighted product method. Now, once we have all these three appraisal scores, all these three individual appraisal scores, we take them and we find out the final appraisal score, which we call as the KI. Okay. So we calculate the KI by using this particular formula. Okay. So now we'll take a small example, and again, this method is widely popular recently, and all these formulas and all these equations you can easily find in the internet, or maybe we can share this PPT also with you. So we'll just see in Excel that how you can use this all these formulas to get meaningful information from your data that you have. Okay. So let me go to the Excel environment. So now this is the first example that I have taken. So this example I have taken from one of our recently published papers, which was on CoCoSo method-based optimization of cryogenic drilling on multi-wall carbon nanotube reinforced composites. Okay. So let me give a small introduction about this topic. So basically in this, what we were trying to do was that we had some composite plates or some composite laminates, and in which we were doing some drilling in the cryogenic environment. And then there were 4 different kinds of responses which were generated. There were 3 different kinds of process parameters. Drill type was one of the process parameters, feed rate and spindle speed. These are the 3 different types of process parameters that we have, or the input parameters that we have. And using this experimentally, we find out these 4 the process responses. Okay, we found out these 4 process responses. They were basically the delamination factor at entry, the delamination factor at exit, the circularity error, and the surface roughness. Okay, so we found out these values. We did a L27 experiment, and we found out these values. Once we have these values, then as you know, for all the MCDM methods, we do not care much about the input parameters. We only deal with the output or the response parameters. We basically need only this response parameters or the output parameters to form our decision matrix. Okay. So once we have this decision matrix, once we have calculated the decision matrix by using our experimental values, these are the experimental values. So I have saved some time. I've just copy pasted it here. So these are the values that we have. Okay. So the excuse me. Okay. So so we have the values here. So from A1 to A27, these are the 27 different experiments that we have conducted, or in MCDM terminology, we'll call them as the alternatives. Okay. So these are nothing but basically the 27 experiments that we have conducted, and in MCDM terminology, we'll call them as the alternatives. So I've named them as A1 to A27. Okay. Next, I have the 4 different criteria here. So what were the 4 different criteria here? The 4 different criteria were the delamination at entry, delamination at exit, the circularity error, and the surface roughness. So in the MCDM terminology, I'm just using the same terminology here, which is consistent with other MCDM publications. So I'll just say them as C1, C2, C3, C4. So C1, C2, C3, C4 are the 4 criteria. These are nothing but the objectives. So all these objectives that I have in this case are minimization type. It means lower is better. Okay, means I want to reduce the delamination factor. I want to reduce the circularity error. I want to reduce the surface roughness. Okay, so that is why here the optimal type I have written as minimum. Okay, I want to minimize all of them. Again, I have put weights here. So these weights in the original method, in the original paper that we have written, in that we have used different kinds of weights. But just here for the sake of understanding, I have taken equal weights. Okay, this is by far the simplest method that we have. Equal weight simply means that you assign same amount of weight to all the criteria, irrespective of their whether they are maximization type or minimization type. You give them all the same amount of weight. Okay, so that is what I've done here: 0.25, 0.25, and so on. So if you have calculated, suppose say the weight by any other method, suppose say by Merrick or by suppose say SWARA or any other method, so you can put those values here. If you have calculated those, you can directly put that here, and this Excel sheet will take care of all that. Okay. So now I have these values here. So the first thing that we are going to do is that we are going to normalize them. Okay. So let us go back to our equations. So as you can see here, we are dealing with non-benefit criteria. Okay. So for the non-benefit criteria, what we have to do? We have to do maximum minus the individual cell value divided by the range. Okay. So it is good to find out the minimum and the maximum and the ranges here. So I'll just put equal to here, and I'll write min. So MIN is a inbuilt function available in the Excel sheet. So I'll use that. And once I have that, what I'll do is that I'll use F4. So by using F4, I will lock this particular row, okay, or particular column. I will lock it, okay, or I'll lock it from number 4 or row number 4 to row number 30. Okay, so I'll lock it here. Okay, so I have it here from row number 4 to row number this, and then I can simply click here and I can drag it, and now you'll see that it will calculate the minimum for all the different rows. Okay. Similarly, what I'll do is that I'll take this first one and I'll drag it here. Again, I'll see that again it has calculated a minimum, but actually I wanted the maximum, so I'll just go here and edit it as max. Okay. So max is the default function that we have in our Excel to calculate the maximum of any given row or any given column. So in this case, we are calculating the maximum value of this column by using the max command. Okay. Again, simply to save our time, what we'll do is that we'll just drag it. Okay. If you want to just check, you can double click here and you can see that this is the current row it is dealing with. Next, we'll find out the range. we know that range is nothing but the maximum minus the minimum. So what we'll take is that maximum minus minimum. We have found out the range, and then we'll just again drag it. So now we have all the values. Okay. So we have now calculated the minimum, maximum, and the range. So if you remember from this particular formula, to calculate the normalized value, what we have to do is that we have to take the maximum. We have to take the maximum value of that particular column. Okay, so this is the maximum value of this particular column. So I'll lock it. Okay, again I want to lock that particular cell. So I'll take this minus this one. I'll put this in a bracket and I'll divide it by the range. I'll divide it by the range. Again, range is also locked for that particular column. So I'll lock it for that particular column like this. Okay. So again, I've locked the it is maximum minus the cell entity divided by the range value. Okay. So if you just drag it like this, again, if you drag it like this, these are some of the shortcuts that I'm teaching you so that you save a lot of time. So again, you see automatically the formula is implemented to this as well, right? So since all of these are minimization type, you can just drag it. Okay. In the next example, we'll see when we have what we'll do when we have mixed kind of goals. But here the goals are all minimization type. So once we have this, what we'll do is that we can just drag it down up to A27, and we have all the normalized values here. Okay, very easy. Till now it is very easy, right? So next what we'll do is that the next step is we'll just take the weighted normalized value. So again, what is the weighted normalized value? The weighted normalized value is nothing but the product of the individual criteria weights multiplied by the entity in each of the columns. Okay, so I'll just take this. I will take the weight, and weight here is a constant for each column. So I'll again lock it by using the F4 command, and then I'll use this, and I'll drag it down, drag it across. So here again, you can check it like this. Okay, you see here by red box and this one that it is implementing. Okay, everything is correct. So next, what we can do, we can again drag it down. So by doing this, again we have calculated the weighted normalized matrix. Okay, so here simply what we have done is that we have multiplied the normalized matrix with the weight value of each of the criteria. Next, as I told you, that this method is nothing but the amalgamation of the weighted sum method and the weighted product method. So what we are going to do now is that we are going to find out the index value of the weighted sum method, or the appraisal score of the weighted sum method. So what was the formula? The formula was this. It is simply the summation of each given row. Okay, it is simply the summation of each given row. So I'll just put the command sum here, and I'll just drag it from here to here, and I'll close it. Okay, and I'll just drag it down. Similarly, here also I have what I have done. I know that I am going to need these values later. So what I have done here is that I have calculated the minimum value, just like I have shown here. I calculated the minimum value of this column. I calculated the maximum value of this column, and I calculated the range of the the sum of this particular column. Okay, I'm going to need these values later, so I've already calculated this. These are simple formulas that we have already used in our earlier steps. Okay, next we are going to find out the PI value. For finding out the PI value, we need to first find out the Rij raised to the power Wj. Means we need to find out the exponential weight normalized or exponential weight normalized matrix. Okay. So for this, what we'll do is that we'll take each of the normalized value and we'll raise to the power of the weight. Okay. Or again, the weights in this case are constant, so we need to cell log them. So we have logged them here. Okay, by using the F4 command, and I'll drag it across. Now, again, you can see that this raised to the power, this value, similarly, this entity raised to the power C2, the weight of C2, this raised to the power the weight of C3, and so on. Okay. Next, what I'll do is that I'll just drag it down, and everything is implemented. If you want to check for any of this, you can just see. So this raised to the power, this one. Okay. Next, what we'll do is that just like here, we will do the summation here. Okay. Since I didn't do any blocking here, and it was for 4 rows, and this it was for 4 columns. This is also for 4 columns. So instead of typing, I can just copy paste it here. Okay, you can also type it. If you see, it has just taken the same formula because it was the same as this one. Okay, so you can use this kind of shortcuts while you are doing your Excel sheet, so that you save a little amount of time. Okay, so now here we have the summation of this row. Again, we will take the summation of this whole thing row wise. And again, I have calculated the I have calculated the minimum of this particular row. I have calculated the maximum of this row, and I have calculated the sum of this row, because I know that I am going to, as per the formulas, I am going to need this, the minimum, maximum, and the summation of this row. Okay. So till now, whatever we have done is basically we have done only two methods. Those two methods are this method from here to here. What we have done is the WSM method, or the weighted sum method. And from here to here, what we have done is the weighted product method. Okay. So these are very old legacy kind of methods. So we have just used them. Now comes the actual part of CoCoSo. So in which they use the SI value and the PI value, and they find out three different rankings initially, which are the KA, or three different appraisal scores initially, KA, KB, and KC. And then they combine all these three, KA, KB, and KC, to find out the K value, or the final appraisal score of the CoCoSo. Okay, so let us look into these formulas. So let us look into equation number 6. So equation number 6 says that you take the summation of the SI value plus the PI value, then you divide it by the sum total of the SI and the PI. Okay, it is again very easy. So what we'll do is that we'll take this one plus this one and put them in a bracket. Okay, we'll not log them because these are variable quantities for each row. But what is the constant quantity here? So before that, let me put a bracket here, and inside the bracket, I'm going to take the sum of this plus the sum of this. Okay. Now, if you remember from the formula that this is coming in the denominator, in the denominator we have the sum of the SI values, or the SI column, and we have the sum of the EFA column. Okay. So this is a constant quantity. So again, I'm going to lock it. Okay, I'm going to lock the entire thing by using F4 command. Okay, I have logged the entire thing. So now I can just drag it down, and I will get the value of all the different alternatives. Okay, for all the L27 alternatives, I have the value. So here again, you can verify for any of this. Okay, so you see it is taking this plus this divided by this sum and this sum. Okay. Now you can individually calculate the rank of this by using the rank command. You take the rank command, and you take this value, you put comma, and you take the entire range that you have. Again, this range is a constant for this particular given column. So again, you have to lock it by using F4. Okay. Now, if you just drag it down, so you will have the rankings of the different alternatives as per the K value. Okay. So this is generally in CoCoSo we rely only on the K value, but in the original paper they also gave the rankings of the K value to see that how the different K parameters, so KIA, KB, and KIC are affecting the rankings. Okay. So to look into that, they also give this kind of a individual value by each of these appraisal scores. Okay. Now we will calculate the KIB value. So this KIB value is simply the SI value, or the individual cell value of SI divided by the minimum of that particular SI. Okay. Similarly, we have the PI divided by the minimum of the PI. Okay. So it is very easy. So what we'll do is we'll take SI divided by the minimum value, and we'll lock the minimum value because it is a constant for this particular question. So similarly, we'll have the PI divided by the minimum value. Again, we'll lock it because it is a constant for this particular problem. So we have this KB value. Okay. So this is the formula that I use: SI divided by minimum of the SI column, and PI divided by minimum of the PI column. Okay. So this value, this is the simply value that I have taken, or this is simply what I have done. And now, if you want to do it, you can just drag it down. Okay. You can drag it down, and you can again validate. You can see that it is taking the same values. Okay. Next, again, we want to find out the rank, but again, finding out the rank, we have the same formula. So either you can again type rank and all these things you can do, or either you can just take from here and you can copy and paste it here. So once you copy and paste here, it will show you value any, because what you have done here is that if you see here, you have taken this value, but you have taken this range. Okay, so now you have to just pull this range from here to here. Okay, if you want to do it like this, you can do it like this, or if you want to just type, okay, I'll just type it also. If you want, you can just type rank, and you can take this, and then again, so you can take this entire range, and then you can lock it. Okay, it's the same thing, but if you just copy and paste it, will save a little bit of time. And again, writing formulas again and again, sometimes you may make some mistakes. So this is the rank of rank as per the KB appraisal score. Okay, by using KB appraisal score, we have got this new rank. So interestingly, till now, what we have seen that for this particular set of problem, the A16 is giving the same rank or is getting the best rank as per both the KA parameter and the KB parameter. Okay, it is getting the best rank as per both of this. Now let us see what happens in KC. So in the KC, the lambda parameter that I'm talking to you, it comes into play here. So it is simply lambda multiplied by the SI value plus 1 minus lambda multiplied by the PI value divided by the lambda multiplied by the maximum SI value divided by the plus 1 minus lambda multiplied by the maximum PI value. And it is easy to implement. So we'll write it here. We'll put lambda. Here I have written the lambda value. I have taken the default value as 0.5. We'll see later that how we can just change it and what are the effects of this value on your analysis. So I've taken this lambda value. I'll again this lambda value for this particular problem is constant. So let me lock it, and then you multiply it by the SI value. Okay. Then you take the 1 minus lambda value. Again, lock the lambda value because it is constant, and you multiply it by the PI value, and this entire thing is your numerator. Okay, this entire thing is your numerator. If you want, you can have one more bracket here. So this is your entire numerator part. Okay, so similarly in the denominator part, what we'll have? We'll have the same thing. We'll have lambda multiplied by the maximum of SI. So we'll take lambda, which is again a constant, multiplied by the maximum value. Okay, again here this is also a constant. The maximum for this particular column is a constant. So again, I'll add 1 minus lambda as per the formula, lock it, and then multiply it by the PI value, the maximum of the PI value, and this is also a constant. So again, I lock it here, and I will give an additional bracket here. Okay, so this is my implementation of this particular formula. Okay, so I've implemented this particular formula, lambda SI plus 1 minus lambda PI divided by lambda max SI plus 1 minus lambda max PI. I've implemented this here. Now everything is cell locked. Okay, everything by using this dollar symbols, I have locked it to the entire to the respective entities. So now again, what I can do is that I can drag it down. Okay, even if I drag it down, then it will hold the computation. Okay, so you can see that it is taking the same value that I wanted to. Okay. Now again, as I told you earlier, you can just copy paste it from here to find out the ranks. So again, it is showing NA because you have used this particular column. So instead of this, you need to use this particular column, and now you have the rankings. Okay. So now you have the rankings as per the KC parameter. Okay. So here you see that for both for all three KA, KB, and KC, you are getting this alternative as the best. But for the other alternatives, there is a slight change. For example, alternative 1 was ranked number 17 or ranked 17 by KA, but whereas when we are using KB, it was ranked 16, and but when we are using KC, it was ranked 17. Okay, so as Dr. Prasenjit also discussed in the previous section, that generally we are interested only in the best output. Okay, maybe we are interested only the best output and the worst output, because worst output tells us that be away from this particular response, and the best output is something that we desire. Okay, so generally we look at the robustness, or we look at the best output that or the best response, and see that it does not change with respect to the computation. Okay, when we carry on the computation from one part to another part, it should not change. That is what we generally desire in our MCDM methods. Okay, so here for all of these three, Ka, Kb, and Kc, we see that it is giving the same rank, okay? Or this getting best alternate number 16 was getting the best one. Okay? Next, we will calculate the final candidate final Ki value, which is basically an amalgamation of all these three individual values KIA, KIB, and KIC. So initially, what we do is that we take the cube root of this. Okay? KIA, KIB, and KIC. We raise it to the power of 1/3. So basically, we are taking cube root of this, and then here we take the summation and we take the mean of this. Basically, this is the mean of all these three, and this is the cube root of all these three. Okay. So we will implement this here. So initially, we want to find out the cube root of all these three parameters. So KA multiplied by KB multiplied by KC, and we want to find out the cube root. So I use 1/3. Okay. So this plus the mean. Okay, we want to find out the mean of this. Okay, or the average of this three. Because 1/3 means because there are three different values, so we are trying to find out the average of this three. So again, what we'll do is 1/3 multiplied by the sum of this three, Ka, Kb, and Kc. Let me put an extra bracket here. Okay. So that's it. So now we have implemented the final formula where we have found out the value of Ki, which is nothing but the cube root of the product of all these three entities and the mean of these three entities or these three appraisal scores. And then we drag it down and we get the values. Okay. So here you should remember that in all of these three, K, A, KB, and KC, and in fact K also, we are expecting for higher values. Okay, so whichever is having the higher value, that is considered the best alternative. So here, as you can directly see that this rank or alternative number 16 is having a value of 10. Okay, so it is the best rank alternative. So if you just look into all of the other values here, so you'll see that 10 is by far the best value as compared to maybe its nearest value is somewhere between 8.6. Okay, so it means that this alternative A1 is outperforming its nearest alternative by quite a margin. Okay, it means that this method should be robust, or what will happen is that even if we change the value of the weight and the lambda, there should not be. It is expected that there should not be much changes in the final ranking. Okay. So again, for final ranking, I'll just copy paste it here, or you can use the formula also. So I'll just drag this column from here to here because I'm taking the rank with respect to this particular column, and I'll just double click. Or I'll just drag it here, and then I have the final ranking. Okay. So we find out that this particular alternative 16 is our best rank so far. Okay. So now comes into the picture, or in this particular CoCoSo method, we have two different entities that we should talk about, or we should whenever we want to find out the robustness of this method, there are two different aspects that we should talk about. The first one is the weights, which are in any other method also. In any other method also, when you want to find out the sensitivity or the robustness, you try to vary the weights and you see what is the overall effect on the final ranking. But here in CoCoSo, we have an additional parameter called the lambda. Okay. So as I told you earlier, that lambda is nothing but some kind of tuning with respect to the SI and PI, means the weighted sum method and the weighted product method. Okay. So you can just change the value of lambda and you can find out whether the values are changing or not. If the values are not changing, then you can say that the ranking that we obtained for this particular set of results or for this set of data is quite robust. Okay, so let us do that exercise. Since I have already parameterized the entire Excel sheet, so I can just change the value here and it will give me a corresponding value. So for 0.1, there is no change. For 0.2, there is no change. And similarly, you can keep on trying for the other values. So you can see that when I'm changing the value of lambda, there is no change in the value of the final alternative. Okay. So now this is how you generally solve the CoCoSo method. And in this CoCoSo method, what we saw, or in this particular example, what we saw was that all of these were like minimization type of problem. Okay, I've taken a problem from our recently published paper, and all the factors or all the criteria were minimization type. But if you want to do the same thing for another example, so I have another example here. So this another example was initially given in the initial paper that was published in 2018. So this is the original paper where Mortaza Yazarni and his group showed the or developed this particular method, CoCoSo method, and they have depicted the method for a particular, I think, green supplier selection problem. Okay, so they have taken a small problem of green supplier selection. So this is a logistic provider, or basically it is a supplier selection problem. So in this supply selection problem, what they have done is that they have seven alternatives or seven different suppliers, and they are considering five different criteria, out of which one criteria is minimization type, and the other four criteria are the maximization type. Okay, so other four criteria are the maximization type. This is the minimization type. Okay, so the only difference between the previous example that I've solved, sorry, this one, the previous example that I've solved, and this particular example, I've already solved this. So let me show it here. Is that there is only going to be one particular change, which is the calculation of the maximum values. For this, we are going to use this particular formula: max minus xi divided by the range. Okay. Only this is the difference. Just every other step is same as it is. Okay. Every other step is same as it is. So it means only in the initial normalized matrix you need to change the formula for calculating the normalized values of the maximized or the maximum type of criteria, and remaining everything is as it is what we have done in the previous example. Okay, same everything, same process. Okay, again here also you have the lambda values. In this example also you have taken the lambda values. So again you can play with this lambda values, and you can see whether by changing this lambda values the ranking is changed or not. Okay, so you see that there is sufficient amount of robustness in the method that even by changing the lambda values, there is no significant change in the, or there is no change in the final ranking. Okay. Similarly, what you can do is you can also look into the different criteria. For example, criteria weights. For example, here this criteria weights 0.036, 0.192, 0.326, 0.326, and 0.12. These are already given to us in the particular research paper which the authors have written. So they have already calculated the weights. So if you want, you can again calculate these weights by using different kinds of methods. Maybe you can use the entropy method or Marek method. Marek is the, I think, to the best of my knowledge, Marek is the most recent objective type of weight calculation method. Maybe you can use those kind of methods, and you can calculate the weight value, and you can put it here. So again, I think I will not solve this again because I already have it here, and it is same as it is. Only one set of formula is changing. So let me just delete this, and rather than it, I will show you some other things that how you can report and what to report in the research paper, because I think we are almost we are out of time. So let me just show you what to report in the research paper. Okay. So for this particular, let us first see the original paper. So this was the problem which was solved by the original authors, and they solved it for a supplier selection problem. So let us look into their paper, that what they have reported. So they have reported the original matrix, okay, the original decision matrix, which is typical in any MCDM paper. Then they have reported the they reported the normalized matrix, and then they have reported the weighted normalized matrix, and they have calculated the SI values here. They have reported the SI values also here. Then reported the weighted product method values, and they have reported the final appraisal score of the appraisal score of the weighted product method, the PI values. Then they have reported the KA, KB, KC, as well as the individual ranks. Okay, and they have reported the final rank. So this is what they have reported, and finally from this you get this ranking scheme. This ranking scheme is nothing but based on this, because what is this? A3. A3 is the best one. Then A2. So that is what they have just represented here in form of equation. So A3 is better than A2. A2 is better than A7, and so on. So here they have found out that A3 is the best kind of uh, alternative they have, and A4, A5 is the worst alternative that they have. Then they have done some test and validation for this by changing the weights and so on, by using different kind of weights, weight that I showed you here. Uh, that is what Dr. Prasanjit was also talking about in the last session, that you do some sensitivity analysis. So they have taken 48 different sets of they have taken 48 different sets of weights. So in all this, they have changed the values of the weights W1, W2, W3, W4, W5. They have changed it 48 times, and by taking this 48 different sets of weights, they have solved the problem 48 different times, and then they have calculated these ranking schemes. Okay, they have calculated the ranking schemes, and they have seen that how the rankings are deviating. Okay, for example, here we found out in the example that they've given, the A3 was the best. So here you can see that with respect to the 48 different, so here green is the A3, this green one is the A3. So with respect to the change in the weight, how A3 is deviating. So you see that for most of them, A3 is getting the best rank. It is in the innermost circle, and for suppose say maybe like 20 or 30% of them, it is getting the second rank, and maybe like for very minute part, it is getting the third rank. Okay, so basically they have validated from this sensitivity analysis that the alternative that they have chosen, or the supplier tree that they have chosen, it is going to give them the best result in 70% of the cases. Maybe in suppose say next 25% of the cases, it is the second best answer, and in maybe 5% of the cases, it is the third best answer. But in no case, it is the worst answer, because you do not see any green line going up to here. So it means in no case in no combination of weights, you see that supplier tree is the worst. Okay, so supplier tree is always among the top three. Okay, so it gives a lot of confidence in the if you do this kind of sensitivity analysis, it gives a lot of confidence in your output or in your results, because as Dr. Prasanjit was also talking about, most of these MCDM problems, for example, this kind of managerial problems where you have supply selection and so on, all this have a lot of decision making involved in terms of like manpower associated and cost involved and a lot of time involved. So you cannot change a decision just like that. Okay, so you have to be very sure about what is the decision that you are taking, or what is the final output that you have. So this kind of a sensitivity analysis, it gives you additional kind of backing or the confidence that you need to implement your decision. Okay, so these are the outputs, or these are the ways in which the original authors have depicted their results. This is a typical management problem, or this is from the management side. Let us see how we have reported. We are more from the engineering side. So let us see how we have reported our results. So this is the initial matrix, or the decision matrix that we have, or the experimental plan that we have. And let me just skip through it. So here what we have done is that we have given the decision matrix. Okay, this is the original decision matrix, and this is the normalized decision matrix. Okay, we have put them both in one table to save some amount of time. Next, what we have done is that we have skipped some of the other tables, because we are out of we have paucity of space in this particular paper. So what we did was that instead of just like the original authors, they used 48 different sets of weights. What we did was that we took some standard methods. We took the mean weight method, we took the standard deviation method, we took the entropy method, we took the critique method, and we took the Marek method. We solved this problem by using 5 different methods. We got 5 different sets of weights, and we implemented these 5 different sets of weights, and we found out the rankings for all of them. So basically, in this graph, what we have shown here is that we have shown the normalized appraisal score of the KI, KIA, KIB, and KIC value. Why normalized? Because if you go and look back into this particular sheet, you will find that here the KI value is, or the KI range is very small. It is from 0.0 something. But whereas the KB value is ranging from, suppose say, means it is the maximum value is 26 and so on. Okay, and similarly KC value is also typically between 0 to 1. So if we just plot it in its absolute terms, then we will find then this graph will not be accurate. So what we did was that we normalized them. Okay, we normalized these values. So how did we normalize? We just I just the original Excel sheet here. So I just normalize it by taking this value divided by the maximum of this row. Similarly, KB divided by the maximum of this row, and KC divided by the maximum of this row. Okay, I've normalized it here. These 3 normalized values once we have, and by using this 3 normalized, we have plotted this graph. Okay, so this graph basically tells you that what is the contribution of the KIA, KIB, and KIC in the final ranking. For example, if you look into this case, A16 was your best alternatives. This you see that almost all of them have equal contributions towards the final ranking. Means this is the orange part is the KA, or this part is the KA, the green part is the KB, and the blue part is the KC. So in this particular alternative, you see all of them has almost the KA, KB, and KC. All of them has almost equal contribution towards the final ranking. But if you typically look at some of the other alternatives, for example, if you look at A6, here you see that the contribution of KB is very less as compared to maybe KC and KA. Okay. So this is something that additional that we wanted to project, or this is something additional that we wanted to show. So we highlighted this in form of this kind of graphs. Okay. Additionally, what we have done is that we have given a graph instead of giving the rankings. We have also given the tabulated ranking. Other than that, we have also given this particular graph where basically we showed that in terms of the ranking, in terms of the experiment number or the alternative, which is the best rank. Okay. So you see that here this one we have inverted it. So one is the best rank. So you see that the best rank is got only by alternative number 16 for all the methods. For mean weight, standard deviation, entropy, critique, and merit. For all of this, we got the best rank for one only. So this kind of a visualization chart, it helps you immediately to find out that which are the best alternatives. For example, here you can immediately tell that alternative number 16 is always getting the rank 1. Okay, or maybe this alternative 13 is also a very high rank alternative. It is getting the rank 2 and so on. Okay. So other than that, what we have done is that we have shown the relative correlation between all these different methods. Okay, because we solved it by using entropy method, critique, merit, standard deviation, and mean weight. So we calculated the correlation among the rankings, and obviously, as we have shown here also, that even by changing the rankings, we are getting A16 as the best output or the best response. So the same thing is again validated here, because you see that there is a high rate of correlation. Means the worst correlation is 0.93. Means there is 93% correlation between these methods. Okay, and in some cases we have almost one correlation. Okay, 1:1 correlation means the exact rank are predicted by Merrick as well as entropy. It simply means that by using Merrick-CoCoSo and by using entropy-CoCoSo, you are getting the same rank. That is what it means. Okay. Or if you look at this 99, it simply means that by using critique-CoCoSo and by using standard deviation CoCoSo, you are getting 99% similarity in the ranks. Okay. Then additionally, since we are from the engineering background where we basically deal into parametric optimization. So what we have done is that our objective is not just the ranking. The managerial part or the management people, they are just worried about the final outcome in terms of which is the best rank and which is the best alternative. But generally, we from the engineering sciences, we are not worried only about the best alternative. We are also worried about what is its effect on the entire experiment or our entire problem. Okay. So what we do here is that we have we have taken the appraisal score and we have calculated it for each of the levels. Because if you go and look back into our original data set, where here what do you find? You find that we have drill type and we have three different types of drill type. We have solid carbide, we have a second type TICN coated, and we have a TILN coated. Okay, and similarly here in the feed rate also we have three different types. We have 10, 25, and 40. Similarly, spindle also we have three different types: 500, 1000, and 1500. So what we have done is that uh, we have just taken the appraisal scores and plotted them with respect to this individual levels. We have aggregated it for each level. For each of the level, we have averaged it and then we have plotted it. So what does it tell you? It gives you a value of the optimal parametric combination. For example, from here, from this graph, immediately what you notice that the peak is for TICN coated. Okay, so what does it mean? That TICN coated drills are always going to outperform the solid carbide and the TIALN coated. Okay, so it means that if I've been given a choice between all of these three, I should choose TICN coated because it is getting the maximum appraisal score in all the cases, whether I solve it by mean weight, standard, or anything, or critique or merit, it is always getting the best. Similarly, when I look at the feed rate, I see that it is a downwards kind of trend, which simply means that at 10 at the lowest feed rate, I'm getting the best appraisal score. So it means I should select this value, okay, for my subsequent experiments or for my final output or for my final to report it as a final optimized value. Similarly, I see that a maximum spindle speed, okay, 1500 RPM is giving me the best result. So it means my final combination is what? My final combination is uh, drill type of TICN coated, feed rate of 10, and spindle speed of 1500. Or in MCDM terms, we report it as A2, B1, and C3. Okay, A2, B1, and C3 is the best combination that we have. Okay, obviously we already have a combination, or we already have a combination which we got from the ranking of the 27 parameters. But other than this is another ranking that we have. Okay, or this is additional information that we have. Okay, by looking into the process inputs or by looking into the process parameters, we have this additional input where we find that A2, B1, and C3 is the will always give you the best kind of output. Okay. Then we have always also plotted this graph. So let's not delve into this because it is a little more complicated to draw and little more complicated to explain. So let's not look into the parallel plots. But I think these are some of the simple plots that you can also give in your problems because it will give additional kind of things to explain, or it will give additional insight into your results. Okay. And finally, we have given a comparison table. I think we have given a final comparison table with respect to. Okay, so we have not given the final comparison table here, but we have given in terms of percentage values in the conclusions. Okay, so that's it from my side. If there are any questions, I'll be happy to address them. Hello, hello, am I audible?